So, we are going to study numerical integration today, and it is all well known to anybody who does science or engineering about what an integral is. So, we will see a few techniques to do these perform these numerical integrals in a computer, and how computer handles the accuracy of such integrals. So, integral is nothing but the inverse process of derivative or a differentiation. Or let us write differentiation. So, when we talk about integration, we talk about integration of some function, say it is a function of x between two intervals, say a and b. So, we represent it like this. So, it is between a and b and f of x dx, and this f of x is known as the integrand, and it is some function of x, maybe a polynomial in x, or maybe a more complicated function with exponentials and logarithm, or trigonometric functions of x, and that has to be integrated from a lower limit of a to an upper limit of b, and this is precisely we encounter almost in our daily life these kind of integrations. So, basically if you know the position of a particle as a function of time, let us call it x t, the velocity v t can be found using a simple derivative, which is v of t equal to dx dt and so on. So, just in the same spirit as integration being the reverse of differentiation or the inverse of differentiation, we can find out the, if we know. So, this is for the using the derivative. So, this is using derivative, and in a very similar manner, if we know v of t, then the position x of t can be found using x of t, it is from some 0 to t. Now, I will use a dummy variable t prime, because in the integral the upper limit of the integral is t. So, we will use a dummy variable, basically it is a time variable, but using a dummy notation for that as t prime. So, this is basically we have to find out, and in this particular case, if you compare between the first line that we have written here, here and what we have written here, this a, which is the lower limit, is taken to be the time t equal to 0, that is the starting time, and b is taken as the final time or the ending time, which is taken as t, and this integral has to be done over over this time variable, which is t prime between 0 and t. So, we make a general claim that the evaluation of the integral I equal to f of x dx is equivalent to solving a differential equation. So, basically a dy dx equal to f of x for y at the upper limit b given some value for the lower limit for y at a, we can assume it to be 0 without any loss of generality. So, because of this closeness of these two formalisms, we will take them up one after another. That is, first we will talk about numerical integration, and then we would go and talk about this solution of differential equations. Okay. So, when is numerical integration becomes important, or when it is indispensable in a physical problem. Okay. So, numerical integration techniques are absolutely necessary in the following situations. So, what are the situations? Let us just list them. One is that no closed form for the solutions available. What I mean to say is that, so for example, f of x is equal to exponential minus t square dt and from say 0 to some x. Okay. So, there is no closed form that is available. So, if you need to do this integral for some value of x, you need to do a numerical integration. It could also be that closed forms are available, or closed forms exist, but the solutions are too complicated. Okay. So, if it is too complicated for for us to comprehend what is the nature of this or what is the value of this integrand, or the nature of the integrand itself is quite complicated. So, that even if a closed form is available, it is very difficult to infer any physical feel out of it. We would have to go for the numerical integration. The third, which is probably one of the most important for us, is that the data available for x and y, we write it x and f x. However, no mathematical relationship exists. Okay. This is like you have done an experiment and you got x and y, or x and f x, and you need to integrate this function f of x over some range, and you have no clue what the functional relationship is, and you need to do this integration. Of course, then the numerical integration is the only possible way. So, let us just see what we mean graphically by numerical integration. So, we have to evaluate an integral of the form I equal to a to b f of x dx. Okay. So, what it means is that let us have a f of x, which is say simply like this, and so this is f of x versus x, and say this range or this end is a having a value x equal to a, and say we have a value which is x equal to b, and we need to know by this integral what it means for this particular case is that we need to know the area under the curve. So, an integral always means an area under the curve. So, this is that area under the curve which we have to find out. Okay. So, this shaded area that is shown here is to be found out, and this is what is meant by the numerical integration, and the a and b are shown here. And of course, what we can do is that we can break this whole interval between a and b into several sub intervals such that every interval. So, let me show you a little broader picture. So, let us say only a little bit of f of x is shown. Now, if we make this things make it grid like this and make the grid small enough, so that they each of them look like a say a rectangle or a trapezium or a quadrilateral, then of course, we can find out the area of a quadrilateral and sum all of them up in order to get the area under the curve. So, this is quite easy to do, and you can increase the accuracy of the method by choosing smaller and smaller intervals. So, that if in case of this you choose an interval which is smaller than this. So, let us show it with a different color. If I choose an interval which is smaller than this and so on, then I am going to get a more accurate result, because finally, your f of x is a continuous function and we are discretizing it by making mesh of it, and so these discrete elements that we consider should be as small as possible. Of course, sometimes numerically it is not possible to choose them to be extremely small, because that would probably take a lot of time to integrate, or it could lead to other problems, but ideally we want it to be small, so that we get a better accuracy for this. So, this is a finer mesh, as it is called, is required for this kind of things, for doing this kind of integrals. Even if it looks simple, it still is a very cumbersome process. Why? Because you have to split it up into several trapezoids or quadrilateral and things like that, and the more wiggly the function is, the chances that you will be able to form a quadrilateral, a uniform quadrilateral is questionable, especially when the function is very rugged. So, the other way of doing it is that we can approximate this f of x by interpolation polynomial, and we can do it. So, we will use an interpolation polynomial for f of x. Okay. So, what we mean to say is that your I equal to a to b f of x dx is equal to a to b a p n of x, that is a polynomial, nth order polynomial. Now, I am no longer saying that I am going to use small grids, which eventually I will show that, but this f of x is actually approximated by a polynomial, and then you integrate it analytically. Okay. So, this is the main idea behind this. So, a to b f of x dx is to be replaced by a polynomial this and a to b, and this is written as I equal to 0 to n and a w I p n x I. So, where several things are to be noted here, it is a less than x I is less than b, w I are the weights. Okay. So, this polynomial actually comes with different weights for different regions, and these x i's are called as the sampling points. Okay. So, let us say that this is the, so the integral has to be evaluated using some sum over I and w I and p n x I, and that is the formula for evaluating an integral numerically using numerical methods by assigning weights and interpolating a polynomial. Okay. So, let us see this more carefully. There are of course various ways of selecting the location and the number of sampling points, that is x I, but there are two things that are important for us. One is that when the sampling points are equally spaced. So, what it means is that you have taken data at regular intervals of time, and then all these x I points are equally spaced, and this method is known as Newton-Cotes method. And the second is that when so this is equally. So, when the sampling points are not equally spaced. And this is known as Gauss Legendre. So, we will be mostly talking about these two methods when the sampling points are equally spaced, which is given by this Newton-Cotes method, and when they are not equally spaced, they are given by this Gauss-Legendre method. So, let us just talk about the Newton-Cotes method to begin with. So, discuss first. So, this has very efficient algorithms and they are known as one is the trapezoidal rule. So, which uses this Newton-Cotes method, trapezoidal rule, and we can also use the Simpson's 1/3 rule, 1/3 rule, and as a third Simpson's. So, basically this is called as a 2-point formula, and this is called as a 3-point formula. And finally, the Simpson's 3/8 rule, which uses a 4-point formula. Okay. So, let us discuss one by one, and so let us just start or get ahead with this Newton's formula for interpolation, or Newton-Cotes formula. Let us just write it as Newton's formula for interpolation. So, we have n plus 1 points, those are experimental data points starting from x 0 y 0 all the way till x n y n. So, need to find y n x. So, which is a polynomial of nth degree. And let the values of x be equidistant. So, that is x I equal to say x 0 plus I h, where I equal to 0, 1, 2 and all the way n. So, these data points are equally spaced, as we have said that this is a formula that we are going to derive for equally spaced data points. So, the polynomial can be written as y n x equal to a 0 plus a 1 x minus x 0 plus a 2 x minus x 0 into x minus x 1 a n x minus x 0 x minus x n and so on. Okay. So, this is the polynomial. Since this y n of x that should agree at the tabulated points, we have a 0 equal to y 0, a 1 is just the slope, which is y 1 minus y 0, x 1 minus x 0 equal to delta y 0 by h. A 2 equal to delta square y 0 2 factorial by h square and so on. And if you go, I will tell you what the meaning of was the meaning of delta square, and a to the power n is delta to the power n y 0 divided by n factorial into h to the power n. Whereas, of course, delta is equal to, so we have this can be written as, so our so delta 0 delta square y 0, it is equal to y 1 minus y 0 y 2 minus y 1 divided by x 2 minus x 0 x 2 minus x 1, and similarly delta cube y 0 would be, y 0 should come right here. So, delta cube y 0 would be y 1 y 2 minus y 0 y 2 minus y 1, and so you know, I mean, it will have 3 terms in the numerator, and we will have 3 terms in the denominator, and they are sort of are they are defined in this particular fashion. And then every order you go, you will have more and more terms coming in the numerator and denominator in a multiplicative fashion, and this is what the definition of this is. So, if you substitute these and x equal to x 0 plus p h, then what I get for y and x, which is the approximate polynomial for the data set that has been given to me, it is equal to a y 0 plus a p delta y 0 plus a p into p minus 1 by 2 factorial delta square y 0 plus so on p into p minus 1 p minus 2 and so on. So, this is like a p minus n plus 1 and divided by n factorial, and there is a delta n y 0. Okay. So, that is the nth order polynomial that we are looking for, which could appropriately substitute or replace the f of x that have been found out from the experiment. Okay. So, now we evaluate the integral. Y n x and dx. So, use the above formula for y and x, and so basically this is particularly useful when we do not know what is f of x or what represents what's the mathematical form of f of x. So, I simply now go ahead and substitute this from earlier. So, it is x 0 to x n, and then we have a y 0 plus a p delta y 0 plus a p into p minus 1 by 2 factorial a delta square y 0 plus a p into p minus 1 a p minus 2 by 3 factorial delta cube y 0 and so on, and then there is a dx that is there. So, it is this is your nothing but the y n of x. Now, if you remember, your x is equal to x 0 plus p h. So, that tells you that dx is equal to h dp, and we can replace this there. So, your I becomes equal to x 0 to x n y dx or y n dx. This is equal to h 0 to n. So, this is actually h. Let us write it properly. H, and then you have a y 0 plus a p delta y 0 plus a p into p minus 1 by 2 factorial a delta square y 0 and so on, and then all right. So, let us see that this is of course h into n y 0, because this is just a 1, and then you have a dy here or rather a dp here. So, this is that h dp. So, the first term becomes h n y 0. Okay. The second term can be found out if you just note that 0 to n p delta y 0 dp. So, this is like delta y 0 p square dp from 0 to n. So, this is delta y 0 uh, p sorry, this is p dp, not p square, this is p dp. So, this is p square over 2 0 to n, and this is like delta y 0 n square by 2. So, this will become equal to n square h by 2 delta y 0, and the next term, if you do it carefully, it becomes this by 12 and then the delta y 0 and so on. Okay. So, that is the third term and so on. So, the important thing is that we obtain different integration formula for different values of n. Let us see how. So, where n can be 1, 2, 3 and so on. Okay. Okay. So, let us that takes us to this trapezoidal rule. So, what it means is that we set n equal to 1 in the general formula. So, which means that all differences, that is deltas, will become 0. Y dx, in which case if we put n equal to 1. So, we have 0 to x n, which will now become x 1 because n is equal to 1. This is simply equal to h y 0 plus half delta y 0, and so this is nothing but h. So, this is actually not n, this is h. This h and this y 0 plus a half y 1 minus y 0. So, this is like a h over 2 and a y 0 plus a y 1 and so on. Okay. So, this is for the interval. So, we still have I mean we can divide an interval into between a and b into as many intervals as we want. For the next interval between x 1 to x 2. So, this is between x 1 x 0, or let us call it x 0 and x 1. So, x 1 and x 2. So, this is that x 1 and x 2 will be x 1 and x 2 y dx, which is equal to h, and y 1 plus a half delta y 1, which will be h, and y 1 plus a half y 2 minus y 1. It is equal to h by 2, a y 1 plus a y 2. Okay. So, that is the for the second interval, and for the carrying on with this for the last interval. So, we have broken down So, let us not write this here. So, just write x 1 interval between x 0 to x n into n intervals. So, for the last interval, which is x n minus 1 x n, this is like a x n minus 1 x n, which is equal to h by 2 and a y n minus 1 plus a y n. So, if you take the contribution from all these integrals, you will see that only the first one, that is y 0, and the last one y n, they are counted only once, while all others are counted twice. So, of combining all of these, one gets a y dx between x 0 to x n, which is equal to h by 2 y 0 plus twice of y 1 plus y 2 y n minus 1 plus a y n, and that is the formula for the trapezoidal rule, or it is also called as a multiple trapezoidal rule. So, this is called as a trapezoidal formula for the trapezoidal rule. All right. So, let us see an example of this trapezoidal rule. So, suppose we divide the entire range only into one segment, that is the entire integration is now into one segment. There is a single trapezoidal rule. So, we have a I equal to f of x b to a dx, which is according to the trapezoidal rule, it is h is b minus a, and the average value of f a and f b divided by 2. So, what it means is the following, that you have a curve like this, which is f of x versus x, and this is that x equal to a. So, this is f of a, and say this is b, and this is say f of b. Okay. So, we are replacing this curve by a simple trapezoid, and by using this trapezoidal rule, we are calculating the area of these trapezoid, which is shaded here. So, we are approximating by so basically this curve has been approximated by a straight line, and then we are calculating the area of the trapezoid. So, the integral estimate is given as, so I is equal to width into average height So, this is like b minus a into f a plus f b by 2. Okay. So, that is the average height f a plus f b by 2 and multiplied by the width of this, and this gives you the area under the trapezoid. But this is of course very crude, how crude it is one can understand, but before that let us calculate the error in the trapezoidal rule. So, error of course comes from dropping the higher order terms in the trapezoidal rule, and because we have dropped some terms. So, there is a truncation error that is bound to come in. Okay. So, to remind ourselves of this formula that we have seen, it is x 0 to x n or a to b, whichever way one wants to write it. N by 2 delta y 0 plus a n into 2 n minus 3 by 12 delta square y 0 and so on. Okay. So, the trapezoidal rule is for n equal to 1. So, the second term onwards, I mean basically the the term that are the second term onwards are dropped. So, now the polynomial expression for the forward difference formula is y n x equal to y 0 plus p delta y 0 plus a p into p minus 1 by 2 factorial delta square y 0. So, this can be actually written as t 0 plus a t 1 plus a t 2 and so on. So, in trapezoidal rule, terms from T 2 onwards are neglected. So, the truncation error in trapezoidal rule is E trap for the trapezoidal and T for the truncation. This is A to B a T 2 and a dx, which is f double prime p by 2 0 to 1 p into p minus 1 h d p, which is equal to minus f double prime p and h over 12. Because of this, I mean this is where we have used x equal to x 0 plus p h. Okay. So, your dx dx dp equal to h. So, f double prime p is nothing but h square f double prime x. So, the E trapezoidal and the truncation error is nothing but h cube by 12 f double prime x for a less than x less than b. Okay, so, this is the error in the trapezoidal rule. Let us see some one quick example of this, and so we have to evaluate the integral 0 to 1 exponential x dx by dividing the interval into one say 2 trapezoids and second say for example 4 trapezoids. And the way it can be done. So, let us just do one. So, H is equal to B minus A by 2, which is 2 minus. So, this is not from 0 to 1, say from minus 1 to plus 1. So, it is 2 divided by 2, it is equal to 1. So, I is equal to H over 2 F A plus F B plus H F A plus I H I equal to 1 to n minus 1, and of course, here n equal to 2. Okay. So, this is equal to half exponential minus 1 plus exponential 1 plus a exponential 0. So, if you simplify this, it comes as 2.54308. Now, for the second case, when you consider 4 trapezoids, in which case your H is equal to B minus A by 4, n is 4 here. So, this is like 2 by 4 equal to 0.5. So, I is equal to 0.5 by 2 plus exponential minus 1 plus exponential plus 1 plus exponential 0.5 plus exponential 0 plus exponential 0.5 and multiplied by 0.5, and it came out as 2.39917. Okay. So, the exact, if you calculate I exact, this is equal to 2.35040. Okay. So, this is the exact. By 2 intervals we calculate it to be 2.54308, and 4 interval itself gets us reasonably close. So, so n equal to 4 gives a much better estimate. Okay. So, before we wind up, let us see the error according to the calculation that we have done. So, this is equal to E trapezoidal and a T integral, which is equal to h cube by 12 f, and we calculate the maximum for x for minus 1 less than equal to x less than equal to 1, and this one actually comes out to be like 0.5 cube divided by 12 into e to the power 1 and things like that. So, this is if you calculate it, this will give you the error. So, you will see that the error from the exact value using this interval 4 interval value, that comes out to be pretty close. So, you can calculate the error from the I exact and minus I trap using 4 intervals. So, this is 2.35 minus 2.39 etcetera, etcetera, and then you can divide it by the exact value and multiply it by 100, that will give you the relative percent error. And when you calculate the truncation error from the formula that we have derived, you will get values that are very close. Okay. So, we will carry on with this a little bit more on the trapezoidal rule, and then we will go to the Simpson's rules, that is 1/3 rule and 3/8 rule for calculating these numerical integration. You will see that particularly the Simpson's 1/3 rule is very efficient and is mostly used in most of the numeric computation for using, or rather evaluating integrals.